Hey guys, this is Dr. Calkins. We're going to wrap up week 10 lecture. The easiest way to start, since you don't have the handout I would normally give in class, and to even prevent from even having to maybe load it at all, I'm going to look at page 105 in the lab book. Coming up for experiment 16, we'll see this again. But this is definitely the best and most illustrated version of this idea. What we're looking at specifically is double replacement reactions. So this was that wife swap kind of idea of two married couples and they both trade partners. Just pay attention that A's and B's never get together because they're typically positive metal ions. X's and Z's don't get together because they're typically negative non-metal groups of atoms or just atoms, in this case ions. So as we look, I'm going to kind of zoom into this top corner. These are the solubility rules that just predicts when they're going to be water soluble or not. So as we look in this first little category here, everything in yellow is well behaved. That just means that they're never, ever, ever, ever going to precipitate ever. So if you have any metal cation from group 1, you'll always be water soluble, always be a spectator ion, meaning in the reaction you're going to watch, you're not going to participate, and then you're never going to precipitate. Precipitate's just another fancy word for insoluble solid. So any group 1 metals, the ones that we see in class are typically lithium, sodium, and potassium. Rubidium and cesium are expensive and they're somewhat toxic, so we don't deal with those. If you look down here though, acetates and nitrates, great for water solubility. That's why we use things like lead nitrate before, because we knew it would be safe in that reaction. And then ammonium compounds as well, always safe, always soluble, always a spectator, and never a precipitate. These are going to answer most of those homework questions straight away. As we get a little bit lower though, the issue we have is these are usually mostly soluble, mostly spectators, and mostly never precipitate. So that works great most of the time. The issue is to the right, we're going to have some exceptions. So as we have exceptions, what we're going to see is there are certain metals like lead, silver, and mercury that when they're with silver, lead, or iodide, they're going to precipitate. They're no longer going to spectate, they're going to be water insoluble. So for halogens, we really only watch out for 3 metals. If they aren't there, we're fine. They're going to be soluble, they're going to be spectators, they're going to never precipitate. But if those 3 metals are present with them, maybe in a separate beaker when they're mixed together, then you're going to see that color change. Same thing for sulfates. Look for lead, calcium, barium. Barium's going to be a pretty common one for us, some strontium. But definitely barium sulfate, very common precipitate that we'll see in lab, coming up in a different video. We get to the bottom, it's kind of the reverse idea of what we want. These guys are the ones that always are insoluble, always are going to precipitate, they're never going to watch, they're never going to be a spectator ion. So if you see a phosphate, it's probably a precipitate. Carbonate, chromates, dichromates, sulfides, probably a precipitate. The only time we have to watch out is, well, no doubt, maybe they're attached to those group 1 metals. That's never, ever, ever precipitate, always spectate, and again, never precipitate. So if you're with those group 1 metals, that changes everything. And in particular for a sulfide, calcium can change its mind and make it some water soluble, but again, we probably won't see that one in class at all. Same idea for hydroxides. If you see an hydroxide, it's probably a precipitate, probably insoluble in water. It's probably never, ever, ever going to spectate unless we're back to those group 1 metals. And then we have 2 more exceptions, calcium and barium. So the yellow ones are your friends. Those are the ones trying to tell you who's going to watch. So look for those always because they're going to answer most of your homework. So I'm going to take a quick break and do some examples on some separate paper. Alright, we're back to do some examples with the double replacement reaction. First one we're going to try is taking lead nitrate. Remember the lead's in this case, a positive 2. So we're going to cross that 2 and nitrate's a 1. We also have potassium iodide. K plus, I negative is a perfect match. So in double replacement, we'd expect 2 partners like this with 2 partners, and then they're going to switch. Just remember, plus 2s and pluses can't go together. Negative 1s and negative 1s can't go together. So when we switch, we're going to get lead that used to be a nitrate. It's kind of like they're changing last names. Used to be a nitrate, now it's going to be an iodide. But it's still a 2 charge, so we cross the 2, still a 1 charge, so 1 goes back. And then we have potassium with the leftover, in this case, nitrate, +1, -1, perfect match there. So there's our double replacement reaction. We replace both with their partners. So that was step 1. Step 2 is going to be who is soluble in water and who isn't. So if you look at your list while I look at my list, nitrates, always water soluble. They were the ones in yellow. So anytime this happens, we would say water soluble because of nitrate. And if we're water soluble, we're going to use a aqueous, AQ. Potassium iodide, well, potassium's group 1, just like nitrate was in that yellow, potassium is 2. Group 1 metals are always water loving, so aqueous again. And in reality, they should always be aqueous in front, otherwise there's no point in mixing them together. You don't want to precipitate before they ever have the chance to make a new one. But as they mix, it's kind of like we're in two beakers, much like we were in our first experiment. If we have a beaker here, what it means to be water soluble is in those ions, the Pb+2 ions and the NO3 negative ions, they will separate. That's what dissociation means. If we have a separate beaker, when we stir it up, these disappear into homogeneous solution as well, and we have K pluses and I negatives floating around. And that's what it means to be a solution. And this is what happened in our first experiment. But then when we mix these together into a new beaker, or one or the other, doesn't really matter. Now we're going to see something unique happen. The Pb+2s are going to stay super far away from the K pluses because they're going to repel. The I negatives and the NO3 negatives are going to stay away from each other because they also repel. And they can stay with their partners, but it's kind of like having a party. And this little car going in the party, and this little car, now they're on the dance floor. And you can dance with your partner, or you can dance with other partners. Just remember, negatives and negatives don't dance, and positives don't dance. So sure, lead could dance with the partner that it came with, but it could dance with the new partner that it found at the party. That's what we have to watch out for. Potassium and nitrate could also dance, and we also have to watch out for those. One thing nice about those in yellow, back on page 105 of our lab book, is if you're in yellow, you're never a precipitate ever, always a spectator ion. And we see both of those are now together. Spectator ion. That means they're not going to do anything in water, they're going to stay separated. We just write them in the reaction together because it looks like a grouping when in reality they're not together at all. So spectator ions are water soluble. Really the same thing, just asked in a different way. And spectator ions, again, stay separated. They're basically sitting on the bench. So in a way, nitrate is like the designated driver of lead, and so is potassium for the iodine. What we need to worry about is lead iodide. If I bring the lab book back real quick to double check for you, notice what we find is 4 halogens. Most of them should be soluble, should never precipitate, should be spectator ions, and that's true. That's definitely the case with potassium. But guess who came to the party? One of the 3 exceptions we said to worry about, lead, silver, and mercury, we have to worry about. And who came in this other party was lead. So because we see lead, we know that we're headed for a precipitate. This is one of the exceptions for our precipitates, for the iodide category. So this is a precipitate. It's also going to be water insoluble, and it's going to produce a color change when we mix them together. And that's what we're after in this kind of chapter, to recognize those features. We're going to practice some more in the lab book, but there's another type of double replacement reaction that we're going to cover here in a minute. Don't forget, reactions sometimes need balance. Here we had 1 lead, 2 nitrates, so we're going to put a 2 here, because remember that's a unit, and that applies to the potassium and the nitrate separately. So it does give us 2 potassium, so we're going to come back over here with a 2 to balance it. So double check, 1 lead, 2 nitrates, 2 times the 1 is still 2 nitrates, 2 potassiums. So this is again 2 times that imaginary 1, This is also 2 times a different kind of 1, but in the end the same. And then we have 2 times 1 for iodide, and we already had 2 iodides, so now we're balanced. So one more example, and then we'll do more examples in the lab, experiment 16 later. Alright, so in this case we're going to show the other type of reaction that's typically found, and that's taking an acid, HCl, adding with a base, NaOH, and now we swap the positive, positive 1, positive 1. So we get H with OH, fancy name for water, and we get Na with Cl. So it's still a double replacement kind of reaction. We just have hydrogen pretending to be a metal in our case. It's actually the acid hydrogen. So here we have acid, and here we have base. So a neutralization reaction is what this is called. It's going to be a small portion of this chapter, but it's going to be a larger portion later. And notice when those acids and bases mix together, here was your acid, here was your base, they make water. And water is a liquid, and that's the other type of double replacement reaction we're going to look for. What we saw earlier is sodium, group 1 in the yellow, loves to be aqueous, and it will still be aqueous, So even here we have spectator ions. They're really not together. They're going to be separated. So just pay attention to that idea. Definitely group 1 metals, nitrates, acetates, ammoniums also. Always spectators, always water-soluble. And then again, water is our liquid, not our solids. It's not going to change colors, but when this happens, and we'll see this in lab in a separate video, this will get pretty hot, and that's when we know it's going to work. In our situation here, because we made water, that was really the answer. Let's show you real quick how it works, and then we'll be done with this video. So again, H and Cl go into a beaker. They separate H plus and Cl negative. Sodium and hydroxide separate Na plus, OH negative. And then you have a chance to mix them together. What's funny about this reaction is something that happened to me personally when I was at Truman. Our teacher took acid, threw in a paper clip, and sure enough it dissolved. They took a base, threw some hair from his head in the beaker, and it dissolved, shown on an overhead projector. Document cameras didn't exist back then. So when they mix them together though, he poured them together after seeing that one eats through metal, the other one eats through hair. He poured them together and he drank it. And we're like, he's gonna die. But he didn't, because what happens is H plus and Na plus separate because they're both positive. OH negative and Cl negative separate because they're negative. But when you have a chance to trade partners, all you're really making in the end is salt water. Probably not brave enough to try that myself, because if you get the mixtures wrong, there's still leftover acid or base, which would be very deadly. And he probably sneaked in a clean beaker of water to drink when we weren't paying attention. But in any case, neutralization reactions work just like double replacement reactions. Both have spectator ions. It's just that in precipitation reactions like the ones up here, look for your solubility table, and then down here just look for water when you're dealing with acids and bases. And this will hopefully help in your homework.